In the 20th century, the solar system seemed simple. 8 planets, from Mercury to Neptune, and a 9th, small, cold and distant world, Pluto. For several generations, that nearly invisible dot on school maps marked the end of everything. Beyond it, it was assumed there was only darkness, emptiness and distant stars. The idea of an edge was clear. The last planet was the gateway out of the solar system, but the story was never that simple. Already in the 19th century, the concept of an edge was tied to an uncomfortable problem. The orbits of Uranus and later Neptune did not completely match the calculations. Astronomers detected small deviations. The solution seemed obvious. If a planet deviated, perhaps there was another one farther away, pulling on it with its gravity. Thus, the idea of Planet X was born, a hypothetical world beyond Neptune, invisible to the naked eye, but present in the equations. The discovery of Neptune in 1846 reinforced that logic. Thanks to mathematics, its position was predicted before it was seen. It was a spectacular triumph of Newtonian physics, and it left a silent message. If once it worked to search for a hidden planet to explain anomalies, it could work again. In the late 19th and early 20th centuries, several astronomers looked again at the numbers and thought that something else had to be out there beyond Neptune's orbit. In that context, the figure of Clyde Tombaugh appears, a young man from Kansas without a university degree, hired by the Lowell Observatory in Arizona. His work was patient and repetitive. He photographed the same region of the sky on different nights, compared plates with a mechanical device, and looked for points that moved. The stars remained fixed. Planets and asteroids changed position. In 1930, on one of those plates, Tombaugh saw something. A tiny dot was slowly shifting among the constellations. Pluto had been born. The world received a name associated with the Roman god of the underworld. It seemed appropriate. It was dark, distant and cold. The first calculations gave it a very inclined and eccentric orbit. At times it was closer to the Sun than Neptune. That already made it strange. However, for decades it was treated as the 9th planet, heir to Planet X. Books, encyclopedias and school models repeated that list of 9. The edge of the solar system was at last defined. Soon doubts arose. The initial estimates of Pluto's mass were large. It was thought that perhaps it had a size comparable to Earth, but observations improved. Telescopes became more precise. The behavior of the other planets was measured more rigorously. Again and again, the calculations led to the same uncomfortable conclusion. Pluto was much smaller than initially believed. It could not explain the supposed orbital anomalies. And, to make matters worse, those anomalies also diminished when the masses of Uranus and Neptune were measured more accurately. In other words, the original Planet X ceased to be necessary. The deviations faded into the margin of error. The reason that had driven the search weakened. But Pluto was already there, on maps and in popular culture. It was accepted as the 9th planet, more by tradition than by physical necessity. For much of the 20th century, two ideas coexisted: the romantic image of a small solitary planet at the edge, and the suspicion that the real story was more complex. The next turn came with the technological revolution in astronomy. Digital sensors, larger telescopes, and systematic search programs began to comb the deep sky. In the 70s and 80s, some theoretical models suggested something important. If the solar system formed from a disk of gas and dust, it made no sense that beyond Neptune there would be a total void. Remnants should remain. Small icy bodies, fragments from the construction of the giant planets, condensed into distant orbits. For a time, that idea was only a prediction, a hypothetical population of trans-Neptunian objects. We knew that comets existed, we knew they came from distant regions, but it was still necessary to directly observe that belt of icy debris. Pluto, because of its orbit, seemed to fit better with that family than with the orderly group of 8 large planets, but there was still no proof of its relatives. In 1978, Charon, Pluto's large moon, was discovered. That finding made it possible to measure the mass of the system with precision. The surprise was great. Pluto turned out to be even lighter than expected. It was not a small planet. It was tiny compared even to the moon. The intuition was strengthened that perhaps it did not belong to the same category as the gas giants or the inner rocky planets. Even so, the list of 9 planets remained alive for many more years. The definitive change came in the 1990s. In 1992, a small object was detected beyond Neptune in a stable and distant orbit. It was not Pluto. It was not a visible comet. It was something else. That discovery opened the floodgate. From then on, dozens, then hundreds and later thousands of similar objects began to appear in deep sky surveys. All orbited beyond Neptune. All were icy and small. Pluto ceased to be solitary. It became the most famous member of an abundant population. The idea of an edge wavered again. If there were so many bodies beyond Neptune, the limit of the solar system could not simply be the last planet listed in a textbook. What until then had been seen as a line began to look like a territory, a wide band filled with small worlds, each with its own story. The expression Kuiper Belt began to be used more and more to describe that region between approximately 30 and 50 astronomical units from the Sun. At the same time, bodies almost as large as Pluto were discovered. Some even appeared to be more massive. That forced an uncomfortable discussion. If Pluto was a planet by tradition, what should be done with those new objects? Should planets be added to the list each time a world of similar size appeared? Or should the definition of planet be revised from scratch? The issue ceased to be a technical detail. It affected the way the solar system was taught, the way it was drawn and described. At the beginning of the 21st century, the accumulation of data pushed astronomy to a crossroads. The outer solar system could no longer be described as 8 large planets, 1 small eccentric planet, and then nothing. Observations showed a rich and varied population of icy bodies. The traditional edge had become more diffuse. At the same time, a new image was emerging. Instead of a simple endpoint, we began to see a second band of worlds beyond Neptune. An entire belt of frozen debris. The Kuiper Belt. From Neptune's orbit outward, the solar system changes its appearance. The gas giants are left behind. Sunlight weakens, the temperature drops below 200 degrees below zero. In that distant band, another structure appears. It is not a planet nor a moon. It is an entire population of small icy worlds spread out like a wide ring. That region is known today as the Kuiper Belt. For much of the 20th century, the Kuiper Belt was an idea before it was a direct observation. Astronomers such as Edgeworth and later Kuiper reasoned that if the solar system was born from a disk of gas and dust, It made no sense that beyond Neptune there would be nothing. Formation models indicated that remnants should remain there, bodies too small to become planets, but too large to be simple grains of dust, true debris from the failed construction of giant worlds. The intuition was logical. Closer to the Sun, solid material was abundant. Rocks and metals made it possible to form the terrestrial planets. Farther out, the presence of ices of water, methane, and ammonia favored cores that later attracted large envelopes of gas and gave rise to Jupiter, Saturn, Uranus, and Neptune. In the outer region, however, the formation time becomes longer. The density of material is lower. The rules of the game change. Many planetary embryos never managed to grow completely. They froze in intermediate stages. Today, we know that the Kuiper Belt begins approximately at Neptune's orbit, around 30 astronomical units from the Sun. It extends to about 50 astronomical units, perhaps somewhat farther, like a thick and diffuse band. An astronomical unit is the average distance between Earth and the Sun. That means that typical belt objects are dozens of times farther away than our planet. From there, the Sun looks like a bright point, not much larger than a star. It is not a thin ring like Saturn's, but an entire volume of populated space. Estimates suggest that there could be tens of thousands of bodies, more than 100 kilometers in diameter, and millions of smaller objects, down to sizes comparable to known comets. Each follows its own orbit. Some move in nearly circular trajectories, others travel in very eccentric and inclined ellipses. The result is a kind of second asteroid belt, but made of dirty ice and dark rock. The internal structure of the belt is not uniform. Astronomers distinguish several populations. There are the cold classical objects with nearly circular and low inclination orbits, which seem to have remained calm since the early days of the solar system. There are the hot classical ones, with greater inclinations, marked by gravitational encounters in the past. And there are bodies in resonance with Neptune. These objects complete an integer number of orbits around the Sun for a certain number of Neptune's orbits. Pluto belongs to this group. It is an example of a 3-to-2 resonance, which means that for every 3 revolutions of Pluto, Neptune completes 2. Resonances are not a minor detail. They are the imprint of a deeper process. They indicate that Neptune was not always where it is today. Models of planetary migration suggest that, in the youth of the solar system, the gas giants exchanged energy and moved outward or inward. In that gravitational dance, Neptune would have swept through entire regions of the planetesimal disk, capturing some into stable resonances and scattering others into more eccentric and distant orbits. The Kuiper Belt, as we see it today, is the frozen result of that violent reordering. Beyond the classical and resonant objects, there is another population, the scattered disk. These are bodies with very elongated orbits, which travel far from the Sun and then return. Their trajectories show that at some point they experience strong gravitational pushes, probably from close encounters with Neptune. The scattered disk acts as a bridge between the main Kuiper Belt and even more remote regions of the outer solar system. From a physical point of view, Kuiper Belt objects are a mixture of ice and rock. They contain frozen water, methane, carbon monoxide, and other volatile compounds. Many show reddish or brownish surfaces tinted by complex organic molecules that form when cosmic radiation and ultraviolet light modify surface ices over millions of years. For that reason, Although they are made of common materials, their appearance and color speak to us of a slow chemistry, forged at a very slow pace in extreme cold. Observing the Kuiper Belt is not simple. Its objects are small, distant, and very faint. They reflect little sunlight and move slowly against the fixed background of the stars. Detecting them requires telescopes with a wide field of view, sensitive cameras, and algorithms that compare images taken days or weeks apart. Each new moving point found is a small technical triumph. From just a few pixels, an orbit that may take centuries to complete is reconstructed. Despite these difficulties, the census grows year after year. That changes our image of the solar system. The Kuiper Belt is no longer a curiosity. It is a structural component, a cold reservoir of primordial material, a laboratory where we study what conditions were like at the time the planets formed. Some of its members, when their orbits are perturbed, can become short-period comets that visit the inner solar system. There is one detail that intrigues astronomers. Beyond about 50 astronomical units, the number of detected objects drops abruptly. This is known as the Kuiper Cliff. We still do not know whether that drop is real, a result of how matter is distributed, or whether it reflects the limits of our current surveys. Perhaps there are fewer bodies than expected. Perhaps they are there, but too small or too dark for our telescopes. Solving that mystery is important because it would tell us how much material remains available in the outer regions and how the whole structure formed. The Kuiper Belt is also a key piece for understanding other planetary systems. When we observe around distant stars disks of coal dust and debris, we are probably seeing structures similar to this one, though on a different scale. Our belt serves as a local reference. It is the example we can study in greatest detail. It helps us interpret the faint signals that arrive from dozens or hundreds of light years away. The outer dwarf planets. In the midst of the multitude of icy objects in the outer region, there are a few that stand out, not because they shine more, but because gravity has forced them into a nearly spherical shape. They are not classical planets, nor are they simply giant comets. They are an intermediate category. Today we call them dwarf planets, and several of them live precisely in the belt of worlds beyond Neptune. In 2006, the International Astronomical Union decided to bring order to the definitions. To be a planet, it was no longer enough to orbit the Sun. 3 conditions had to be met: to revolve around our star, to have enough mass for gravity to round the body itself, and to have cleared its orbital neighborhood, meaning to completely dominate the region where it moves. Bodies that meet the first 2 conditions but not the third are classified as dwarf planets. This definition removed Pluto, dwarf planet, from the traditional list of planets, but also placed it at the center of a new family of worlds. Pluto is the most famous example of a dwarf planet. It has about 2,377 kilometers in diameter, 2/3 the size of the Moon. Its orbit is centered around 39 astronomical units, following an elliptical and inclined path that sometimes brings it closer to the Sun than Neptune. It is made of a mixture of ice and rock. Its surface combines frozen nitrogen, methane, and carbon monoxide. Beneath it, scientists believe there are layers of water ice, perhaps with an internal ocean still liquid due to residual heat and tidal effects. For decades, Pluto was a blurry disk even for the best telescopes. That changed in 2015 when the probe New Horizons NASA mission to Pluto flyby 2015 passed at high speed about 12,500 kilometers above its surface. The images revealed a surprisingly active world. Large plains of nitrogen ice without craters indicating young and renewed terrain. Mountains several kilometers high made of water ice, which under those conditions behaves like rock, and a dominant structure, a heart-shaped bright region on the visible hemisphere. Its western half is a basin called Sputnik Planitia, Pluto region, a nitrogen glacier more than 1,000 kilometers wide with convection cells that recycle the surface. Pluto also has an atmosphere. It is thin, composed mainly of nitrogen with traces of methane. It extends hundreds of kilometers above the surface. It freezes and sublimates depending on the distance to the Sun and Pluto's extreme seasons. Ground-based and New Horizons observations showed blue haze layers produced by complex organic molecules formed when solar radiation acts on methane. Recent measurements with the James Webb Space Telescope indicate that this haze plays a key role in Pluto's climate, absorbing and radiating energy and cooling the atmosphere more than simple models predicted. Pluto is not alone. It forms a binary system with its large moon Charon, Pluto Moon, about 1,200 kilometers in diameter. The barycenter of the system lies outside Pluto's body. Therefore, rather than a moon in the classical sense, Charon functions as a companion. Both are tidally locked. They always show the same face to each other. They orbit in about 6 Earth days. In addition, the system has 4 smaller moons: Nix, Pluto Moon, Hydra, Pluto Moon, Kerberos, Pluto Moon, and Styx, Pluto Moon. It is a small planetary system in miniature, located in the Kuiper Belt. The dwarf planet that ultimately forced the redefinition was Eris, dwarf planet. Discovered in 2005, it turned out to be very similar in size to Pluto, but more massive. It is the most massive known trans-Neptunian object. It orbits the Sun on a very elongated trajectory, between about 38 and almost 98 astronomical units, with a period of about 560 years and an inclination of roughly 44 degrees relative to the plane of the planets. Its surface is extremely reflective, almost like freshly fallen snow, indicating fresh nitrogen and methane ices that are renewed when it approaches the Sun. Eris has a moon, Dysnomia. Eris moon, about 150 kilometers in diameter. The motion of this moon allowed precise measurement of the system's mass. The result was clear. Eris has about 27% more mass than Pluto, although it is slightly smaller in diameter. This combination implies a higher density with more rock in its interior. The fact that an object of that size remained hidden in solar system censuses until the early 21st century was a shock. If we accepted Pluto as a planet, why not also Eris? The scientific community's response was to create the dwarf planet category and change the way we think about the outer solar system. Another notable icy world is Makemake, dwarf planet. It is located about 45 astronomical units away, with an orbit less eccentric than that of Eris. Its diameter is around 1,400 kilometers. Its surface shows a reddish color, probably due to the presence of tholins, organic molecules produced by radiation acting on frozen methane. Makemake has at least one known moon. Its characteristics indicate that, although smaller, it shares the same basic mixture of rock and ice as Pluto and Eris, but with a different thermal history that affects how much gas it can retain. Haumea, Dwarf planet is perhaps the strangest of the group. Its longest diameter is about 2,300 kilometers, but it is not spherical. It rotates so fast in about 4 hours that centrifugal force has stretched it into an ellipsoidal shape, similar to a rugby ball. Its surface is covered with very bright water ice. It has 2 moons, Hyakka, Haumea moon, and Namaka, Haumea moon. Additionally, it has a thin ring surrounding the dwarf planet, detected through stellar occultations. This combination of shape, ring, and family of fragments in similar orbits suggests that Haumea suffered a major collision in the past that stripped part of its icy outer layer. Around this core group of classical dwarf planets appear other candidates. Quaoar, trans-Neptunian object more than 1,000 kilometers in diameter, also seems to have a narrow ring very close to the main body, inside a region where simple theories would predict instability. Orcus, trans-Neptunian object, sometimes called the reverse Pluto because of certain orbital parallels, has a moon called Vanf, Orcus moon, Gong, trans-Neptunian dwarf planet, Salacia, trans-Neptunian object, Varuna, trans-Neptunian object, and other intermediate-sized objects complete a continuous gradient. In practice, the boundary between large trans-Neptunian object and dwarf planet is being better defined as we measure sizes, masses, and shapes, but it remains open to revision. Why do all these small worlds matter? Because they preserve memory. By not reaching planet status, they did not clear their orbits nor undergo the same degree of internal differentiation as the large planets. Their compositions and structures tell us about the original material of the outer disk, about how much rock and ice was available, about which volatiles could remain stable at different distances from the Sun. When we compare the densities of Pluto, Eris, Haumea, and Makemake, we obtain clues about how many collisions they suffered, how much material they lost, and how rock and ice mixed in each case. Sedna and the other exiles. Beyond the dwarf planets of the Kuiper Belt, the orbits begin to become strange. They are not just slightly eccentric ellipses, they are trajectories stretched hundreds and hundreds of astronomical units, so long that a single journey around the Sun can take tens of thousands of years. On that outer fringe appears a name that became a symbol of the unusual: Sedna, trans-Neptunian object. Sedna was discovered in 2003 by a team led by Michael Brown. In images from the Palomar Observatory telescope, it was barely a reddish point, moving very slowly against the stellar background. Orbital analysis revealed something extraordinary. Its perihelion, the closest point to the Sun, is about 76 astronomical units. Its aphelion, the farthest point, stretches to almost 1,000 astronomical units. Its full orbit takes about 11,000 to 12,000 years. That means that since writing first appeared on Earth, Sedna has moved only a little along its path. What is most puzzling is not that Sedna is distant. The puzzling part is that it is too far from the giant planets for them to have shaped its orbit. To leave an object with a perihelion of 76 astronomical units, Neptune would have had to push it very strongly. But Neptune dominates well only up to about 30 to 40 astronomical units. Beyond that, its influence weakens. Sedna seems to live in a kind of no man's land. It belongs neither to the classical Kuiper Belt nor to the more distant traditional Oort Cloud. It is a detached object. Over time, other bodies with similar characteristics were found. In 2012, VP113, trans-Neptunian object appeared, also with a perihelion beyond 80 astronomical units. In 2015 TG 387, trans-Neptunian object was discovered, nicknamed the Goblin, and later named Leleku-Honua, with an aphelion exceeding 2000 astronomical units. All share very eccentric orbits and very distant perihelia. This small family is known as the Sednoids. Today, they have only a few confirmed members, but their orbits suggest that many more may exist, because they spend almost all their time in extreme darkness. The inevitable question is, how does an object end up there? One hypothesis is that the Sun did not form alone. It was born inside a stellar cluster, very close to other stars. In that environment, a passing star could disturb the edges of the planetesimal disk. It pushes some bodies inward and sends others into elongated but still sun-bound orbits. Sedna and its relatives would be remnants of that early passage. Dynamic fossils from the childhood of the solar system, marked by a stellar encounter that has long disappeared. Another possibility is that the inner structure of the Oort Cloud, the so-called Hills Cloud, may have played a role. If the solar system ejected millions of small bodies to distances of thousands of astronomical units, some could have remained in intermediate positions between the Kuiper Belt and that spherical cloud. In that scenario, Sedna would lie on the slope between the domain of the giant planets and the domain of galactic tides and perturbations from other stars. Its orbital parameters would be a trace of how that transition was built. The most famous hypothesis is that of a large distant planet, the so-called Planet 9, hypothetical outer planet. The idea, proposed in 2016 and later refined, is elegant. If a planet several times more massive than Earth exists, on a very eccentric orbit, with a semi-major axis of hundreds of astronomical units, its gravity could cluster the orbits of several extreme objects. The statistical alignment of the perihelion directions of Sedna 2012 BP113 Leleku-Honua and other very distant trans-Neptunian objects would appear to point in the same direction, as if they orbited under the influence of a single invisible gravitational shepherd. That hypothesis is not closed. As more extreme objects are discovered, the picture becomes more complex. Some recent results, such as the finding of bodies with very long orbits that do not fully fit the expected pattern, have led to revisions of statistics and models. Alternative explanations have also been proposed. For example, that the apparent orbital clustering may partly be an observational bias. We tend to find objects in regions of the sky where telescopes look more frequently. If this effect is not properly corrected, the signal of a distant planet could be weaker than it appears. In parallel, teams are searching directly for the possible planet. They explore archives from old infrared satellite missions. They develop algorithms to detect points moving extremely slowly in images separated by years. Some studies have even proposed candidates that might be that object, though none has been confirmed. It is expected that next-generation observatories, such as the Vera C. Rubin Observatory in Chile, will help close the question, either by finding that huge distant planet or by demonstrating that the real orbital distribution can be explained without it. Meanwhile, Sedna continues its silent journey. Today it is still approaching its perihelion, which will be reached toward the end of the 21st century. Even at its closest point, the Sun from there is nothing more than a very bright star in an almost black sky, the surface temperature is so low that gases freeze easily. Saturn's surface is probably covered with mixtures of ices and organic compounds reddened by radiation. It is a completely inaccessible world with current technology, but its orbit, traced from far away, is already forcing us to rewrite the dynamic history of the outer solar system. The messengers from the end of the world. When we think of visitors from the outer solar system, they almost always appear. Comets. Small nuclei of ice and rock that spend most of their lives in darkness and from time to time plunge toward the sun, develop a bright coma, and form a tail that can stretch millions of kilometers. They are spectacular to the naked eye, but their importance goes far beyond aesthetics. Each comet carries information about distant regions that we cannot visit yet. They are natural samples from the edge of the solar system. A typical comet has a nucleus only a few kilometers in diameter. It is not a large object compared to a planet or even many moons. It is a porous mixture of water ice, carbon dioxide, carbon monoxide, methane, and other volatile compounds, together with dust and rocky fragments. When far from the sun, this nucleus is dark and stable, like a frozen piece of asphalt. As it approaches, solar radiation warms the surface. The ices sublimate, passing directly from solid to gas, dragging dust and creating a temporary atmosphere around the nucleus. This envelope is the coma. From the coma, tails are formed. One is a dust tail, wider and curved, pushed by solar radiation pressure. The other is an ionized gas tail, straighter, shaped by the solar wind and the magnetic field. The tails always point roughly in the direction opposite the sun, regardless of where the comet is moving. This geometry allows scientists to reconstruct trajectories and estimate how the solar wind and interplanetary environment interact with expelled material. Based on their orbits, comets are divided into two major families. Short-period comets complete one orbit around the Sun in less than 200 years. Their orbits are usually roughly aligned with the planetary plane. Many belong to the so-called Jupiter family because Jupiter, planet, dominates their dynamics. All evidence suggests that this group comes from the Kuiper Belt and the scattered disk. There, small gravitational perturbations from Neptune and other giants send icy bodies inward, where Jupiter further shapes their orbits. Long-period comets are different. Their orbits can last tens of thousands or even millions of years. They arrive from all directions, not just from the ecliptic plane. That nearly spherical distribution was a key clue. In the 1940s, Jan Oort proposed that they must come from a distant reservoir with an approximately spherical shape surrounding the solar system in all directions. That reservoir is the Oort Cloud, hypothetical outer solar reservoir. Although we have never observed it directly, the statistics of long-period comet orbits strongly support its existence. In this scheme, the Kuiper Belt and the scattered disk act as the main source of short-period comets. They are flattened disks linked to the planetary plane. The Oort Cloud would be the great long-period reserve, extending to thousands or tens of thousands of astronomical units. These two regions store material left over from planetary formation. They are cold deposits of blocks that never became planets. When some external perturbation removes them from stable orbit, they become visitors. They fly inward, pass near the sun a few times, and eventually disintegrate or are expelled from the system. Comets are also interesting because of their chemical content. They are time capsules. They preserve ices and organic compounds that formed when the solar system was a disk of gas and dust. Analyzing their composition helps answer questions about the origin of water and organic molecules on Earth. Some measurements of hydrogen isotopes in the water of certain comets do not match Earth's ocean composition well, indicating that water-rich asteroids also played an important role. Even so, comets remain reasonable candidates for having delivered part of the volatiles and complex molecules that made prebiotic chemistry possible. On a geological scale, comets are also a risk. A nucleus only a few kilometers across impacting a planet can release energy equivalent to millions of nuclear bombs. Earth's history shows traces of violent impacts. Not all were comets, many were asteroids, but the basic mechanism is the same. A good reminder of this energy was provided by the comet Shoemaker-Levy 9 comet in 1994. The comet, trapped by the gravity of Jupiter, planet, fragmented, and its pieces collided with the giant planet's atmosphere at tens of kilometers per second. The impacts left dark spots more visible than the Great Red Spot and generated plumes rising thousands of kilometers. It was the first time we observed in real time a collision of that scale between two bodies in the solar system. That event reinforced an important idea. NASA missions have shown that giant gas planets act partly as shields. They capture or deflect comets and asteroids that otherwise might cross the inner planetary orbits more frequently. The same gravity that sent many bodies outward during the infancy of the solar system also clears, to some extent, the current environment. It is not absolute protection, but it reduces the direct impact rate in the region where Earth, Venus and Mars are located. In recent decades, concern about potentially dangerous impacts has led to the development of planetary defense concepts. Most efforts focus on near-Earth asteroids because they are more numerous and more detectable than long-period comets. Nevertheless, the techniques we test work for both types of objects. In 2022, the DART mission, NASA Asteroid Impact Test 2022, was the first practical test of deflecting a small body through a controlled impact. The spacecraft deliberately collided with the moon Dimorphos, asteroid moon of the asteroid Didymos asteroid. The impact changed its orbital period by more than half an hour. It was a successful demonstration that a well-calculated push can alter an object's trajectory. This type of mission is based on something comets have taught us for centuries. Orbits can be perturbed. A close encounter with a planet, the cumulative action of gravity from many bodies, or even the asymmetric thrust of gas jets escaping from an active nucleus can change a comet's path. What is a potential threat to us is, for solar system dynamics, a natural consequence of having many masses interacting over billions of years. The invisible ice ocean. Let us imagine the solar system again from far away, very far away. Beyond Pluto, dwarf planet. Beyond the Kuiper Belt, outer solar system region. Even beyond extreme orbits, such as that of Sedna, trans-Neptunian object. At that distance, the planets no longer matter. They are tiny points orbiting an equally tiny star. However, even there, the Sun still dominates. Its gravity continues to hold a huge reserve of small icy bodies. That reserve is called the Oort Cloud, hypothetical outer solar reservoir. The Oort Cloud is a very solid hypothesis. We do not see it directly. With current telescopes, individual objects would be too small and too dark. What we do see is the indirect evidence. A slow but constant rain of long-period comets arriving from all directions of the sky. They do not come preferentially from the planetary plane. They come from above, below, and the sides. For that to occur, the source must be almost spherical, a sphere of icy bodies surrounding the Sun in every direction. Estimates place the Oort Cloud between about 2,000 and up to 100,000 astronomical units from the Sun. The outer part could reach close to 1 light-year in distance. That is a fraction of the distance to the nearest star, Proxima Centauri, nearest known star to Sun, which is a little more than 4 light-years away. In other words, the Oort Cloud occupies a significant portion of the space between the Sun and its closest stellar neighbors. From the center, the Sun appears as a bright point, but it no longer dominates the stage alone. Current models usually divide the structure into 2 components: the inner cloud, or Hill's cloud, inner Oort cloud region, would be a denser, flatter region, extending perhaps from a few hundred to several thousand astronomical units. The outer cloud, the one we usually imagine as the classical Oort cloud, would be nearly spherical and occupy greater distances. The first would be more closely tied to the plane of the original protoplanetary disk. The second would be the result of billions of years of gravitational perturbations that gradually rounded the distribution. How did something like this form? The story is linked to the violent childhood of the solar system. In the first few 100 million years, when the giant planets were still settling into place, there was a huge number of icy planetesimals orbiting in the region where the Kuiper Belt lies today, and even closer to the Sun. The gas giants, Jupiter, Planet, and Saturn, Planet, acted as gravitational catapults. Each close encounter with one of these giants could launch a small body outward at high speed. Some of those bodies were ejected from the solar system forever. They escaped the Sun's gravitational attraction. Others remained in very elongated orbits, gravitationally bound, but with semi-major axes of thousands of astronomical units. Over time, the combined pull of passing stars and the galaxy itself through what we call galactic tides deformed those orbits. The result is this large diffuse cloud. It is as if the solar system had breathed outward and inflated a bubble of icy debris around itself. The amount of material there is uncertain. Estimates vary. There could be hundreds of billions of objects 1 kilometer or larger. There could be mountain-sized bodies and even some comparable to dwarf planets, but in orbits so distant and slow that we have not yet detected any directly. The total mass, in any case, would be small compared to that of the planets. The Oort cloud is vast but extremely low density. On average, the distance between objects could be tens or hundreds of millions of kilometers. It is a very dispersed swarm. What keeps this structure bound is a delicate balance. The Sun's gravity is strong enough for those bodies to remain attached, but it is weak enough at those distances that any external disturbance can have noticeable effects. The close passage of a star, a change in the gravitational field of the galaxy as the Sun orbits the center of the Milky Way, even the collective influence of giant molecular clouds, all of these can slightly tilt an orbit, compress it, or stretch it. Occasionally, one of these perturbations deflects an object enough that its perihelion approaches the Sun closely. The body then becomes a long-period comet. It descends from the periphery, enters the planetary region, develops coma and tail if it carries enough volatiles, and for a time becomes visible from Earth. After the passage, it may return outward toward the Oort Cloud with a modified orbit, or it may be ejected from the solar system if it has a close encounter with a gas giant. Each comet we see is a statistical sample, one more point in the pattern confirming that at the edges there is an immense reservoir. The Oort Cloud is also in contact with the galaxy in another, more subtle sense. At those distances, the solar magnetic field and solar wind have almost lost their strength. The environment begins to resemble interstellar space rather than solar space. It is the region where the heliosphere stops imposing its conditions and the interstellar medium begins to dominate. Because of their distance, objects in the cloud spend much of their lives in this interface zone. They are bodies physically inside the solar system, but immersed almost completely in the galactic environment. From the standpoint of planetary formation, the Oort Cloud is a kind of archive. It preserves a sample of the original planetesimals, but heavily mixed and redistributed by billions of years of dynamics. Studying its population would tell us, for example, what fraction of those bodies formed in the gas giant region and was expelled, and what fraction may have come from neighboring star systems in the stellar cluster where the Sun was born. It is possible that some Oort Cloud objects are immigrants captured from disks of other systems when young stars were still very close to each other. At this moment, our farthest probes, such as the Voyager 1 NASA Interstellar Probe and Voyager 2 NASA Interstellar Probe, have not even reached the expected inner boundary of this cloud. They are near the heliopause. They have crossed the solar wind boundary, but are still a little more than 100 astronomical units from the Sun. Compared to the tens of thousands of astronomical units of the Oort Cloud, this is only the first step. At current speeds, a probe would need tens of thousands of years to reach the regions where the cloud population becomes denser. It is a territory that, in practice, we can explore only through gravity, statistics, and patience. There is another way to think about the Oort Cloud, not as a sharp edge, but as a transition zone. Closer in, the planets dominate the landscape. Farther out, the galaxy takes control. The cloud occupies that compromise band. It is simultaneously part of the solar system and part of the local interstellar medium. Inside it lie the debris of planetary formation, but their orbits are shaped by external forces. It is a reminder that the solar system is not isolated. It is a substructure within something larger. If we ever manage to directly observe a typical Oort Cloud object in its original environment, we will learn not only about that body, but also about the galactic context in which the solar system formed and evolved. Meanwhile, we rely on reading between the lines. We observe long-period comets. We adjust models. We simulate millions of orbits on computers. Everything points to the same general picture. Around us, at unimaginable distances, float countless icy worlds in slow and fragile orbits. The heliosphere, the Sun, not only floods space with light, it also fills it with particles. From its corona emerge continuous streams of plasma that escape at high speed. This flow is called the solar wind. It is composed of protons, electrons, and light nuclei traveling at hundreds of kilometers per second. Near Earth, it can reach between 300 and 800 kilometers per second. It is so tenuous that there are only a few particles in each cubic centimeter, yet it extends in all directions and pushes the surrounding environment as it moves. While the solar wind maintains this supersonic speed, it dominates the space around the Sun. It fills a large bubble in which conditions are determined by our star. That bubble is the heliosphere, solar wind-dominated region. Inside it, the solar magnetic field and the solar wind shape space weather. Outside, the local interstellar medium dominates. An even more tenuous gas, mixed with dust, magnetic fields and cosmic rays coming from the galaxy, fills that region. The boundary between both is not a rigid wall, it is a transition zone with several layers. As the solar wind moves away from the Sun, its pressure decreases. It spreads over an ever larger volume. At some point, the pressure of interstellar gas and magnetic field begins to resist it. The supersonic flow can no longer expand freely. A moment arrives when the velocity drops below the sound speed in that plasma. There a stationary shock wave forms. That is the termination shock. Heliosphere boundary region. In that region, the solar wind slows down, heats up, and becomes compressed. It is the first sign that the bubble has an edge. Beyond the termination shock, the solar wind becomes subsonic. It does not stop suddenly. It enters a turbulent zone where it mixes with the interstellar medium. That intermediate region is called the heliosheath, outer heliosphere region. In it, the magnetic field becomes twisted, complex structures form, and energetic particles accumulate. Observations from the Voyager 1 interstellar probe and Voyager 2 interstellar probe suggest that it is not a smooth fluid, but a foamy environment filled with magnetic bubbles, roughly comparable in size to Earth's orbit. The outer boundary of the heliosphere is the heliopause. Heliosphere outer boundary. There, the pressure of the solar wind and that of the interstellar medium reach equilibrium. Beyond this point, the solar wind can no longer push outward. Space is filled with particles and fields whose main origin is the galaxy. At that frontier, three clear changes are expected: a sharp drop in particles coming from the Sun, an increase in galactic cosmic rays, and a change in the dominant magnetic field direction. That is exactly what was recorded by spacecraft crossing that zone. For a long time, the heliosphere was thought to have a comet-like shape, a bow facing the direction of the Sun's motion around the galaxy, and a long tail opposite it. More recent observations, especially from the IBEX mission, Interstellar Boundary Explorer, force this picture to be revised. Data suggests that the heliosphere may be more compact and rounded than previously thought, with a shorter and more complex tail region. IBEX also detected a kind of ribbon or band of energetic neutral atoms surrounding the heliopause, a structure still under detailed interpretation. Another interesting feature is the so-called hydrogen wall. As the solar wind collides with interstellar gas, it compresses incoming neutral hydrogen atoms. Decompression creates a region where neutral hydrogen becomes denser and can emit characteristic light. The New Horizons NASA planetary exploration mission had already suggested its existence. Later, measurements of Lyman alpha brightness from New Horizons reinforced the idea that there is indeed a faint hydrogen wall at the edge of the heliosphere. It might seem that this boundary is very far away. However, in cosmic terms, it is still near. The Voyager probes crossed the heliopause at about 120 astronomical units from the Sun. That is less than 1/1000th of the distance to the nearest star. Beyond the heliosphere, the Sun's gravity still dominates. Objects in the Oort Cloud remain gravitationally bound to it. The heliopause marks the effective end of the solar wind, not the end of gravitational influence. It is a physical and environmental boundary, not an absolute cut in the Sun's domain. All of this has direct consequences for Earth. The heliosphere acts as a partial shield against galactic cosmic rays. It does not block them completely, but reduces the flux. The solar wind and its associated magnetic field deflect part of these high-energy particles. Changes in the size and shape of the heliosphere linked to the solar activity cycle and variations in the interstellar medium can modify how many cosmic rays reach the vicinity of our planet. It is one more factor within long-term space climate. Our picture of the heliosphere is based on 3 types of data: direct measurements from spacecraft traveling outward, observations of neutral atoms formed at the boundaries and returning inward, and numerical models simulating the interaction between solar wind and interstellar medium. Continuous comparison between theory and measurement has produced several surprises. One of them was the real distance to the heliopause. Many models placed it farther away. The fact that the Voyager probes found it earlier forced revisions of assumptions about interstellar medium pressure and plasma physics in the helio sheath. The ambassadors of the penumbra. When we look at the heliosphere in a diagram, everything seems clean and abstract. Lines, boundaries, layers. But to truly know what it is like, we had to go there. We had to send spacecraft that moved away from the planets, crossed the bubble of the solar wind, and continued into the interstellar medium. Those spacecraft exist. They have been traveling for decades, and today they are the farthest messengers humanity has built. The first to attempt it were the Pioneer 10 NASA Deep Space Probe 1972 and Pioneer 11 NASA Deep Space Probe 1973. They were simple probes compared to today's spacecraft, but they opened the path. Pioneer 10 was the first human-made object to cross the asteroid belt and fly past Jupiter, planet. Pioneer 11 did the same and also visited Saturn, planet. After their encounters, both spacecraft continued flying on escape trajectories. Over time, their power sources were exhausted. Communication became increasingly faint. The last useful contact with Pioneer 11 occurred in 1995, when it was about 44 astronomical units from Earth. Pioneer 10 maintained the link a little longer. The last telemetry was received in 2002. The final contact attempt in 2003 detected no signal. In practice, both probes became ghost ships of interstellar space, following their courses without being able to speak to us. The baton was taken by the Voyager 2 NASA Interstellar Probe and Voyager 1 NASA Interstellar Probe. Voyager 2 launched in August 1977. Voyager 1 launched in September of the same year. Their primary mission was ambitious: to exploit a rare planetary alignment of the giant planets to perform a tour of the outer solar system. Voyager 1 flew past Jupiter and Saturn. Voyager 2 visited Jupiter, Saturn, Uranus and Neptune, becoming the only spacecraft to have seen those 4 giant worlds up close. After completing those encounters, both entered escape trajectories. What followed is known as the interstellar mission. In August 2012, at about 122 astronomical units from the Sun, Voyager 1 crossed the heliopause, heliosphere, outer boundary. It was the first spacecraft to enter the interstellar medium outside the direct solar wind bubble. The instruments recorded exactly what theory predicted: a sharp drop in solar-charged particles, an increase in galactic cosmic rays, and changes in the dominant magnetic field. Definitive confirmation came in 2013 after detailed data analysis. At that distance, sunlight takes almost 17 hours to reach the spacecraft. Voyager 2 repeated the achievement in 2018, but through the southern hemisphere of the heliosphere at about 119 to 120 astronomical units. Comparing both entries showed that the heliopause is not a perfect sphere. It is an irregular frontier that bulges and compresses depending on direction and on changes in solar activity and the local interstellar medium. Today, Voyager 1, NASA interstellar probe, is the most distant human object. It is more than 160 times the distance between Earth and the Sun, with a communication delay of nearly 1 light day. The radioisotope generators powering it weaken year by year. However, NASA teams have selectively turned off instruments to save energy and keep key sensors active, especially the high-gain antenna. In 2025, they even reactivated an orientation thruster that had been turned off for 2 decades, slightly extending mission lifetime. It is expected that at least 1 or 2 instruments may keep functioning into the 2030s. After that, the spacecraft will continue its silent journey toward the Oort Cloud, hypothetical outer solar reservoir. At human speeds, that journey is desperately slow. Although Voyager 1 has left the heliosphere, it is still very far from any star. It would take tens of thousands of years to reach 1 light year of distance, and more than 70,000 years to approach as close as we are now to Proxima Centauri, nearest known star to Sun. But on another scale, it has already crossed a fundamental boundary. Its instruments now directly measure plasma, magnetic fields, and cosmic rays of local interstellar space. Each data packet that arrives is a sample of the environment surrounding the solar system as a whole. In parallel, another probe follows a different route outward. New Horizons, NASA planetary exploration mission. Launched in 2006, it was designed to accomplish something astronomers had dreamed of for decades: a close flyby of Pluto, dwarf planet. The spacecraft used a gravitational boost from Jupiter in 2007 and, after nearly 10 years of travel, passed just over 12,000 kilometers above Pluto's surface in July 2015. For the first time, we saw that icy world in detail: mountains of water ice, nitrogen plains, and a bluish atmosphere. After the encounter, New Horizons continued deeper into the Kuiper Belt. Its second major target was Arrokoth, Kuiper Belt object, a small cold region object. The flyby occurred on January 1st, 2019. Images revealed a 2-lobed body joined together like a flattened snowman, a contact binary. Later studies suggest it formed by the gentle merging of 2 smaller objects during the infancy of the solar system at speeds of only a few meters per second. It is an almost perfect example of how the first planetary building blocks may have assembled. Today, New Horizons continues its path through the Kuiper Belt. At more than 60 astronomical units from the Sun, it keeps measuring dust background, gas, ultraviolet light, and particle environments at the solar system's periphery. Its energy also comes from a radioisotope generator. Current plans aim to keep it operational at least until the end of this decade, while it gradually leaves the densest region of the belt. Each year, the spacecraft adds a new horizontal layer of data about how space changes at those distances. Not all missions toward the edge consist of flying far away. Some spacecraft remain near the Sun and look outward using neutral atoms coming from the boundary. The IBEX mission, Interstellar Boundary Explorer, has mapped the heliosphere for years through energetic neutral particles produced when the solar wind collides with the interstellar medium. These maps revealed the existence of a curious bright ribbon around the heliosphere, whose interpretation is still under discussion. The successor to IBEX is already underway. The IMAP mission, Interstellar Mapping and Acceleration Probe, launched in September 2025, has just begun its science phase. It is equipped with 10 instruments to study the solar wind, energetic neutral atoms, and interstellar particles. Its goal is to build a more complete picture of how the Sun connects with the interstellar medium, how the heliosphere's protective shield varies, and how energetic particles are accelerated at that frontier. IMAP will not leave the solar system. It will orbit near the Sun-Earth L1 point, but will see the boundary through the messengers arriving from there. If we put all these missions together, a coherent picture appears. The Pioneer probes open the road outward. The Voyager probes actually crossed the heliosphere and entered interstellar space. New Horizons explored the Kuiper Belt from within, visiting icy worlds that were once only points of light. IBEX and IMAP from near Earth trace the invisible contour of the solar bubble through particles arriving from the frontier. They are not science fiction spacecraft. They are modest instruments, many designed with decades-old technology, but they connect something fundamental, what we measure here in Earth's neighborhood, with what happens hundreds of astronomical units away. Debris disks and astrospheres. Until now, we have looked at the edge of our solar system, but the Sun is only one star among many in the galaxy. If it has a Kuiper Belt, Oort Cloud and heliosphere, it is reasonable to ask, does the same happen in other systems? Are there other edges out there, cold rings and stellar wind bubbles surrounding distant stars? The answer, to a large extent, is yes. We do not see the small bodies one by one. What we see is the dust they produce when they collide. Those grains absorb stellar light and re-emit it in the infrared. This was how, in the 1980s, the IRAS Infrared Astronomical Satellite 1983 mission first detected infrared excesses around apparently normal stars. The extra emission did not come from the star itself. It came from debris disks. Today we know that about 20 to 30% of nearby stars show this type of signal. These are called debris disks. They are distant analogues of our own Kuiper Belt, outer solar system region, and, in some cases, also of the asteroid belt. The idea is simple. After planet formation, a population of planetesimals remains, something like raw comets and asteroids. These bodies collide, fragment, and continuously generate dust. Without replenishment, the dust would disappear relatively quickly, dragged away by radiation and effects such as Poynting-Robertson drag. The fact that we see dust today implies that there is an active reservoir of larger bodies feeding it. Dust temperatures provide clues about distance from the star. In many systems, that temperature corresponds to tens of astronomical units, distances comparable to those of our Kuiper Belt. We do not see a full Oort Cloud because it would be too faint, but we do observe cold rings that resemble an amplified version of our own icy band. Some studies speak directly of exo-Kuiper belts. In the closest and brightest cases, we have gone beyond simple infrared access and resolved the disk shape. Observatories such as the Atacama Large Millimeter/Sub-Millimeter Array and the Hubble Space Telescope have captured images where rings and gaps are directly visible. One classical example is the system of Fomalhaut stellar system with debris ring. There, a narrow, eccentric ring of coal dust is observed at about 140 astronomical units from the star. The ring shape suggests the presence of one or more planets shepherding the material, in the same way that Neptune is thought to have sculpted parts of our Kuiper Belt. Other systems show even more complex architectures. There are disks with multiple rings, wide gaps, and marked asymmetries. In some, the ring is displaced from the star. In others, dust clumps appear that could be the signature of hidden planets. ALMA, with its ability to observe in millimeter wavelengths and resolve fine detail, has been key to mapping these structures. In systems such as HD 53143, Stellar Debris Disk System, and 49 Ceti Young Star Debris Disk, ALMA images reveal cold disks with eccentric shapes, internal cavities, and residual gas. In 49 Ceti, carbon monoxide gas has even been detected in abundances suggesting the continuous destruction of volatile rich bodies similar to comets. When we compare these debris disks with our Kuiper Belt, outer solar system region, clear similarities and differences appear. The basic similarity is scale. Many extrasolar cold disks are located at tens of astronomical units, where Plutinos and classical objects live in our system. The difference is dust quantity. Most observed disks contain orders of magnitude more dust than our current Kuiper Belt. They are more similar to the primordial Kuiper Belt, when there were many more bodies and collisions. This is logical. We tend to observe systems that are in a more noisy phase of their history because they are brighter in the infrared. This suggests that our system may be relatively quiet or discrete. Surveys of sun-like stars indicate that very bright cold disks are not the norm around mature stars a few billion years old. Many systems probably have more modest comet belts that are invisible with current technology, similar to or even less massive than our Kuiper Belt. The very luminous dusty edge appears to be a transient phase in planetary system evolution. Debris disks also tell us something about planets we cannot see directly. Fine structures in the dust, asymmetries, narrow rings, and gaps are difficult to explain without planets gravitationally sculpting the material. In that sense, dust acts as a tracer. It reveals where giant planets might be, how far away they are, and how eccentric their orbits may be. Just as Neptune left its signature in the resonances of the Kuiper Belt, exoplanets leave their signature in extrasolar debris disks. The other side of the comparison is stellar wind bubbles. If the Sun has a heliosphere, other stars with winds and magnetic fields should have astrospheres. Again, we cannot send spacecraft there, but we can detect their effects in background light. In some cases, the Hubble Space Telescope has observed ultraviolet hydrogen lines with additional absorption that cannot be explained only by the interstellar medium. These extra absorptions are consistent with a hydrogen wall formed where stellar wind collides with surrounding gas, the equivalent of our own hydrogen wall near the heliopause, but seen from outside. These studies indicate that the heliosphere is not an exception. It is one astrosphere among many. Some appear larger, others smaller, depending on wind strength and local interstellar density. In very active stars, the wind can inflate wider bubbles and offer stronger shielding from cosmic rays for any planets inside. In stars with weak winds or embedded in dense gas regions, the astrosphere may shrink and leave planets more exposed. For habitability, this detail can be as important as the distance to the star's temperate zone. Seen from this perspective, our edge is no longer an isolated case. The Kuiper Belt, the Oort Cloud, and the heliosphere form a concrete example of something more general: planetary systems surrounded by cold debris belts and stars encapsulated in wind bubbles within the interstellar medium. The observed variety, from delicate disks to very massive and asymmetric rings, tells us that the history of each system can be very different. Different collision rates, different migration histories, and different levels of protection from cosmic radiation. Knowing those other edges brings us back home with a new question: how will our own edge change with time? What will happen to the Kuiper Belt and the Oort Cloud when the sun grows older, swells into a red giant, and finally expels its outer layers? The destiny of our distant worlds. The solar system is not a fixed photograph. It is a very slow movie. What we call the edge today will not be the same in hundreds of millions of years, and it will be unrecognizable in billions of years. To imagine that future, we must stretch the scale of time enormously, far beyond human history and even far beyond the lifetime of the Earth as a habitable world. Let us begin with the region we know best, the Kuiper Belt, outer solar system region. Today we see it as a reservoir of icy bodies, with a few prominent dwarf planets and a multitude of smaller objects. Over time, this belt will continue to erode. Each collision between two large bodies generates fragments. Those fragments collide again and are pulverized into dust. Part of the dust is slowly dragged inward by solar radiation pressure. Part is expelled from the system through gravitational interactions. On billion-year timescales, the belt will become less massive, more tenuous, and harder to detect from outside. Something similar happens with the scattered disk, the region of highly eccentric orbits beyond the main Kuiper Belt. Its eccentric trajectories are more vulnerable to gravitational nudges from Neptune, planet, and occasionally from other giant planets. Each time an orbit crosses critically with a giant planet's orbit, the body may be deflected inward as a short-period comet or expelled permanently. The result is a constant trickle. The scattered disk feeds the inner solar system while slowly emptying itself. On very long timescales, it is a transitional structure rather than a permanent one. The Oort Cloud, hypothetical outer solar reservoir, will probably have a different fate. Being so far away, it is less exposed to the internal planetary dynamics. Instead, it is more sensitive to the passage of nearby stars and to galactic tides. Each time a star passes relatively close to the Sun, star of solar system, it slightly alters orbital distributions in the cloud. The effect is not dramatic in a single passage, but it accumulates. Over billions of years, such perturbations can strip a significant fraction of the cloud's bodies, releasing them into interstellar space. The cloud gradually becomes frayed. In the opposite direction, the Sun can also capture bodies during close encounters with other stars. This means that the future Oort Cloud will not be composed only of original solar system material. It will be a mixture. Some of the objects orbiting very far away may have been born around other stars and later changed ownership during the early life of the stellar cluster where the Sun formed. Such mixing probably already exists today. In the future, it will become more complex. In the long term, the Oort Cloud is less an orderly archive and more a mixed deposit of galactic debris. Over this slow evolution, a larger event is superimposed, the transformation of the Sun itself. In about 5 billion years, the hydrogen in the solar core will be exhausted. The star will expand and become a red giant. Its luminosity will increase. The boundary of the temperate zone will move outward. The inner planets will change or disappear. Earth, planet, if it remains in orbit, will no longer be habitable. Mercury and probably Venus will be engulfed or scorched. The inner solar system will be completely rewritten. This change will also affect the edge. As it expands, the Sun will lose mass. The gravitational pull it exerts on planets and small bodies will decrease. Orbits will gradually open up. All semi-major axes will increase. Some marginal objects in the Oort Cloud, which today are barely bound to the Sun, will escape more easily. Others will move into wider and slower orbits. The effect is similar to loosening the rope holding the bodies together. The gravitational size of the solar system will grow in terms of distance, but its effective control over the most distant objects will be weaker. After the red giant phase, the Sun will expel its outer layers and become a white dwarf Sun remnant. It will be a small, hot remnant, roughly the size of Earth, but with a significant fraction of the original solar mass. From that moment on, luminosity will slowly decline over billions of years. There will be no intense solar wind like today. The heliosphere, in its current sense, will disappear or shrink into a much smaller bubble. The boundary defined by the heliopause, heliosphere outer boundary, will no longer have the same meaning. In that scenario, the solar system will mainly become a system of remnants. Some gas giants may survive in wider orbits. Some minor planets, asteroids and comets may continue to exist. The Kuiper Belt, if anything remains of it, will be extremely dispersed. The Oort Cloud will be less populated and more mixed with the galactic environment. The edge will no longer be marked by a sharp change in stellar wind, but by the distance at which the weak gravity of the white dwarf can still retain some bodies against perturbations from neighboring stars. From our perspective, however, these spacecraft are marks in history. They are the first artifacts to cross the heliopause and enter the interstellar medium carrying human information. They bear plaques and discs with data about who we were when we launched them. They do not change the dynamics of the solar system's edge, but they change how we think about it. For the first time, the boundary is not only something we measure from afar. It is a place we have touched with instruments built on a small planet orbiting a medium-sized star. If we could freeze time and look at the solar system from outside, we would see a star wrapped in a faint bubble, surrounded by an almost invisible crown of icy bodies. There would be no wall, no exit door, only gradients, smooth changes, transitions. The edge is ultimately a concept that we draw onto a continuous process, yet exploring it teaches us something essential. Even in the most distant places where sunlight is only a spark in darkness, the history of our star and our planets continues to leave traces, and understanding those traces is part of understanding who we are and where exactly our cosmic home begins and ends.